You've probably seen some of the stunning images released by the James Webb Space Telescope. Those vast star fields, glowing nebulae, and gravitationally warped galaxies that seem almost too perfect to be real. But behind the beauty, Webb is quietly capturing something far more mysterious, something NASA wasn't expecting, something the agency couldn't fully explain even after months of analysis. And the truth is, the anomaly Webb detected was never meant to be headline news. In fact, for a short time, it wasn't mentioned publicly at all. It began during a routine observational campaign aimed at studying a relatively ordinary galaxy group. Webb collected data, as it always does, across multiple infrared wavelengths. Engineers expected the usual mixture of starlight, dust signatures, and gravitational lensing. Instead, in one corner of the field, there appeared a strange structure, faint, compact, and unlike anything in the rest of the image. At first glance, it looked like a tiny ring of light surrounding a dim core. That alone wasn't unusual. Gravitational lensing can create similar shapes. But this object behaved differently. It wasn't tied to any known galaxy or cluster. It wasn't the result of foreground mass bending distant light. And it wasn't moving with cosmic expansion like the objects around it. It simply sat there, bright and still, defying every category astronomers use to classify celestial phenomena. NASA initially described it as an instrument feature, a common placeholder meaning we don't know what this is yet. But over the next week, researchers repeated the observation from a different angle. The anomaly remained. They repeated it again with a separate filter, still there. A third time using a different set of calibrations. The ring didn't change shape, brightness, or position. That's when NASA quietly flagged the data for deeper review. An unexplained structure, stable across multiple exposures, visible in raw files, and confirmed by independent teams, is incredibly rare. And when Webb scientists realized the anomaly didn't appear in any previous surveys, not even in Hubble's deep fields, they understood that this might be the first time humanity has ever seen this object. I'm Alex McColgan, and you're watching Astrum. Today we'll explore what JWST found, why NASA hesitated to explain it, and how this anomaly might change our understanding of the universe. To understand what makes this anomaly so unusual, we need to look at how the James Webb Space Telescope interprets the cosmos. Webb observes the universe in infrared, a type of light perfect for peering through dust, revealing structures that once remained invisible. Usually, when Webb encounters a new object, scientists can match its signature to a familiar category. Starlight curves in predictable ways, dust absorbs at known wavelengths, and galaxies have characteristic shapes depending on age and composition. But this anomaly matched none of these. Its spectrum showed a strange combination of thermal emission and absorption, almost as if the object was both warm and cold at the same time. It radiated like a dust cloud, yet didn't scatter or block surrounding light. It absorbed like dense material, yet had no mass signature strong enough to influence stars nearby. And perhaps most puzzling of all, the object maintained a perfect circle of brightness around its center, something gravitational lensing typically produces only on far larger scales. Small-scale gravitational arcs are nearly impossible. They require an incredibly compact, incredibly massive object. Yet Webb detected no such mass. NASA's first attempt to explain the anomaly was simple. Perhaps it was a calibration echo created by the telescope mirrors. But calibration echoes shift as the observatory moves, and this feature did not. Then, engineers considered a sensor artifact. But sensor artifacts don't appear in raw data from multiple orientations. Webb's early release science team spent weeks analyzing the anomaly. They rotated the telescope, they changed filters,
They compared data from different detectors. The rings stayed exactly the same. That consistency sent a ripple through the astrophysics community. A few researchers proposed that the object might be a new kind of dark matter concentration, a clump dense enough to bend light, yet small enough to evade detection in previous surveys. But dark matter shouldn't glow, and whatever this was, it clearly did. Others suggested an exotic astrophysical remnant, perhaps a collapsed star with a surrounding dust halo. But collapsed stars don't produce symmetrical rings without distortion. The more data scientists gathered, the stranger it became. What appeared at first to be a tiny, insignificant artifact was, in fact, a perfectly consistent feature with no identifiable source. And that raised the most important question. If this isn't a glitch, then what exactly are we looking at?
One theory proposes that the anomaly might be related to a phenomenon predicted decades ago but never observed directly, a topological defect left over from the earliest moments of the universe. These defects, cosmic strings, textures, and domain walls, are theoretical remnants from symmetry-breaking events that occurred fractions of a second after the Big Bang. If such a feature exists, it could subtly distort space-time without leaving behind matter or conventional gravitational signatures, and the faint ring Webb captured could be the first direct evidence of such a structure. But there are problems with this theory too. Topological defects are expected to influence large-scale structures, not tiny localized regions, and the anomaly Webb found is incredibly compact, almost microscopic on cosmic scales. Another idea is even stranger. Perhaps the anomaly represents an interaction between dark matter and dark energy, two components of the universe we barely understand. If dark matter in that region interacts with itself, a process called self-interacting dark matter, it could theoretically produce heat. That heat might glow faintly in infrared. But such events have never been detected before, and current models don't predict a perfect ring shape. Then there's the possibility that the anomaly is a microlensing event, a gravitational lens created by an object so small that its effect borders on undetectable. In theory, a wandering black hole with no surrounding accretion disk could produce such a ring. But black holes distort the stars behind them, and Webb detected no such distortion. Every explanation fell short. The anomaly was too structured for random noise, too consistent for an artifact, too bright for dark matter, too stable for a transient object, and too small for gravitational lensing. And that inconsistency was exactly what fueled the mystery. In private correspondence later released through academic channels, one scientist described the anomaly as a feature that behaves like something we understand, but exists where nothing should. Other astronomers noted that the ring's brightness profile matched no known astrophysical equation. It was as if the object was following rules we haven't discovered yet. And that realization pushed the investigation into brand new territory. Because if the anomaly doesn't fit our models, then it may be revealing a fundamental piece of physics we've overlooked.
As more data poured in, scientists began treating the anomaly not as an error, but as a clue. Webb's next scheduled observations include full spectrum mapping, polarization measurements, and deeper exposures designed to test whether the ring changes shape over time. If it does, the anomaly could be dynamic, perhaps a transient lensing event caused by a moving, compact object. If it doesn't, we may be witnessing a stationary feature, a permanent distortion imprinted into the fabric of space. Meanwhile, researchers compared Webb's data with older observations. Hubble captured the same region in the early 2000s. At that time, the anomaly appeared only as a faint smudge, barely distinguishable from noise. Ground-based telescopes saw nothing at all. Only JWST, with its extraordinary sensitivity, revealed the ring-like structure. This raises an unsettling possibility. The anomaly may have always been there, invisible until we built a telescope capable of detecting it. And if this is just one such feature, how many more are hiding in the darkness? A few theorists now suggest the anomaly could be the signature of a previously unknown particle field, something that interacts weakly with light and gravity. Others believe it may be an echo of an ancient cosmic event, like a gravitational shock wave frozen in space. The boldest idea, though still speculative, proposes that this could be a gravitational fossil, a leftover imprint from an event so powerful it permanently altered the geometry of a tiny region of spacetime. NASA now openly acknowledges the anomaly, calling it an unexpected signal requiring further investigation. But off the record, several researchers have admitted that this discovery could challenge our models of dark matter, early universe physics, or even the structure of spacetime itself. Webb was built to explore the distant universe, to study galaxies, stars, and exoplanets. Yet one of its most important discoveries may be something much smaller, much stranger, and much closer. An object that isn't matter, isn't energy, isn't a star or dust or gas, but rather a fingerprint of the universe's deepest laws. Whatever JWST found, it is real, it is stable, and it should not exist according to our current understanding of astrophysics. That makes it one of the most exciting mysteries of our time. And as Webb continues scanning the cosmos, this may just be the first of many anomalies waiting to be uncovered. Thanks for watching, and stay curious, because the universe always has another secret.